Okay, excellent. Then welcome to today's session in electrical engineering. I'm still Matthias Magdowski. I'm a talented transient analysis test engineer at the Otto von Guericke University of Magdeburg. And I will share my screen, and then we can, as usual, have a look on the table with our exercise material. And we are in the last week of the semester, last but not least. And the topic is transient circuit analysis, task 34, which is this nice task. And I can remember that there is a recording of this task already from the last year, so we will change it just a tiny bit. I will at first copy it to my drawing program here. And what we will do to make everything exactly similar and still totally opposite is we will change the capacitor into some inductor. And yeah, so instead of this capacitor here, we will have some inductor L, and still we have a source, we have some resistor, the C stands for like charging a resistor, so we are kind of charging the inductor. Once the inductor is charged, we could flip over the switch and then discharge the inductor into this other resistor there, which is a discharging resistor. This is what the D stands for. And yeah, still we can think of what is the maximum charging current, after which time this charging is practically finished, and what is the maximum discharging current, and there we might rather think about voltage. So, and it's maybe more interesting to calculate the time course of the current during charging, but this is what we will do. And at the end, if you have current, you can always calculate voltage and vice versa. Okay, so this is more or less the task. So maybe one question before we actually start to do some calculation is, what does the inductor do, or where is, I mean, some element that stores energy, right? In the resistor, we only dissipate energy, electrical energy, and convert it into heat, and the inductor stores electrical energy. Where exactly is energy stored inside an inductor? In the magnetic field. Yeah, and in some capacitor, it would be stored in the electric field. And so these tasks, why we do them at the end of the semester and not at the beginning? I mean, the circuit does not look too complicated.
Because of the transient behavior.
Yeah, because of the transient behavior, and because now really current and voltage are changing over time, and we are looking for the time functions. We want to calculate these time functions. And this is, from a mathematical point of view, quite challenging, because this means at the end we need to solve, I don't know if it's somewhere written in a task, I think not. Yeah, we need to solve a differential equation. And we just discussed, was this topic in the mathematics lecture so far? No, not really. Yeah. Okay, so anyhow, this is what we are going to do. And before we do so, or yeah, what would be your suggestion for solving such a problem? Or what would be an approach?
Forming mesh equations.
Exactly. So if you're solving an electrical engineering circuit problem like this and you don't know what to do, it's always a valid approach to write down a mesh equation, write down a nodal equation, and write down initial conditions we need later on for the differential equation, yeah, and write down, so the mesh equation, Kirchhoff's voltage law, you have a relation between voltages. The nodal equation, Kirchhoff's current law, you have an equation or a relation between currents. And then we need to have like Ohm's law and some law here at the inductor that gives a relation between current and voltage. Okay, so I will switch back to black. So if we have a current through this resistor, we will also have a voltage across this resistor, URC, and this will be also a function of time. Yeah, here we have not the voltage across, and yeah, maybe I should also rather write a V for the voltage. Yeah, and here we have the voltage across the inductor, and we will also have a current going through this inductor as a function of time. So we could write down a Kirchhoff's voltage law. How would this Kirchhoff's voltage law look like?
RC plus VM minus VS is 0.
Yes, or we could say the voltage of the source, which is a constant voltage. So if we go from this point to this point along this way, should be the same sum of the voltages if we go this path. So it's VRC as a function of time. Yeah, and this should be a small v. This is a capital V because it's constant. This is a time function, so it's a small lowercase v, VL as a function of time. Okay. So then we could write down a Kirchhoff's current law, which is not really necessary in this case. But in this case, how would it look like?
Current is so I source would be ICT.
Yeah. So the current here, if we have the switch to this side, would be the same as this current. So the current on this side is the same as the current through the inductor. Okay, and then we have voltage current relations. And how would these voltage current relations look like? For the resistor?
VRC equals ICRC.
Yes, so the voltage is current times the resistance. And for the inductor?
VL equals L di by dt.
Yeah, so V is L multiplied with the time derivative of the current. So if the current changes over time, then some voltage is induced at the inductor. This is the law of induction that we need here to at the end to get a differential equation that we can solve. Okay, so now we have written down more or less everything that we need. Yeah, and we can check that at the moment we have 1, 2, 3, 4 equations, and we have 4 unknowns because we have 2 currents and 2 voltages. So we have 4 equations, 4 unknowns. It's a nice system of equations that we can somehow try to solve. Okay, now before forming a differential equation and using all the mathematical knowledge that we might have or might not have to solve this differential equation, I would try to invest some time into thinking about what will actually happen here. So I will draw some schematic with, let's say, an amplitude axis for current and voltage, and with a time axis. So this is time, and here we can have voltage or current. And yeah, what we can say for sure is that we have a source voltage that always stays constant. So this is Vs, which is a constant voltage. And it's not really written here in the task because we also changed the task a little bit, but let's say that at the beginning the switch was open, and then we closed the switch. So before the switch was, or before we closed the switch, if the switch was open, then the current at the beginning, of course, should be 0. So if I don't know, if I use this light green color here for the current, which is the same as this current, then the current at the beginning should be 0. And then I could use, I don't know, blue or the other green here, which is maybe meaningful for this voltage. Okay, so we have a constant source voltage and the current at the beginning should be 0. So now what happens? Or what should happen?
Exponential growth.
Exponential growth, but why exponential?
Oh.
Why not linear? And why growth?
Okay. Growth because the inductance as current develops, voltage also develops.
Yeah.
Because voltage.
Okay. Yeah, but are you satisfied with this this explanation? More or less, not really. Okay. So let's think about. We know that this voltage is constant for sure, and that the current at the beginning is 0. So if the current at the beginning is 0, what is valid for the voltage across the resistor here? It should be 0 as well. So I will add some dark green dot there. If this voltage is 0, still we have here a constant voltage. Where is the remaining voltage? Across the inductor. So this voltage here, I will use maybe red for this voltage. And so at the beginning, there must be the full voltage across the inductor. So once we close the switch, let's say, the voltage at the inductor jumps to the full source voltage, because at the beginning the current is 0 and the current cannot jump. If the current would jump, then if we look into this equation, then if the current would jump, we would have some infinite value for the time derivative. And so we would get infinite voltage across the inductor, which does not make sense. This is not physical. Yeah? So this equation tells us that the current in the inductor always smoothly needs to change. Yeah? Smoothly needs to develop. The current at the inductor cannot jump, like the voltage across the capacitor cannot jump, because we just said that the magnetic field stores the energy. The magnetic field depends on the current. And if the current would jump, the energy would jump, which is also not physical, because then you would need to have infinite power to change the energy in an instant of time. Yeah? So this does not make sense. Okay, so we have now the full voltage, the full source voltage across the inductor. So now what happens? We have a voltage across the inductor. Now we can look onto this equation, yeah, and say, okay, now we have a voltage across the inductor. So what should happen with the current?
Increase.
Yeah, there should be now a positive, if we have a positive voltage, there should be a positive time derivative of the current. So the current should increase. So I will take my color for the current and say, okay, now the current will increase. If the current increases, what happens to the voltage across the resistor? It increases as well. Yeah? So if the current increases, this voltage increases. So the voltage increases as well. If the voltage across the resistor increases, what happens to the other voltage? This decreases, because the source voltage is constant, and the sum of these two voltages must always be the source voltage. So in the same amount as this voltage increases, this voltage must decrease. Yeah, so that the sum of the two is still the source voltage. So now if the voltage across the inductor decreases, this voltage decreases, what happens?
The current also has to decrease.
No. The current still increases, but slower. The derivative changes. The current still increases, but the derivative, the slope, is getting smaller. And so the current now, too much, but just increases like this, a little slower. And so in the same way, the voltage across the resistor increases a little slower, and in the same way the voltage across the inductor decreases a little slower. Yeah, and now you can imagine what happens. Now we continue this, and then we get this. It's still increasing it's still increasing, but it's increasing slower and slower and slower and slower and slower and slower, but it will eventually reach full current. And in the same way, also the voltage across the resistor increases and increases and slower and slower and slower, and will eventually reach the source voltage. And then, of course, the current across the inductor decreases and decreases and decreases. And in the same way as this decreases, also the slope of the current decreases. And you just mentioned, like 5 minutes earlier, that this is some exponential growth and exponential increase, and maybe this current, this voltage here shows some exponential decrease. Why it's exponential?
Because it's one solution of the characteristic generally.
Yeah, because, I mean, we just said that in the same way how this voltage increases, or let's say in the same way how this current increases, yeah, this current here, also this voltage increases, and in the same way as this voltage increases, this voltage must need to decrease so that they have the constant source voltage. So, and here the derivative of the current is proportional to the voltage. So we are looking for some function, for a function of time, where the function and the first time derivative or the first derivative of the function are equal. And for which function is this the case? For the exponential function. Yeah, and that's why the exponential function is so important in engineering, and maybe also in mathematics, because the derivative of the exponential function is once again some exponential function. So the exponential function is a solution of what we have not yet written down, but what we more or less see already, a solution of a first-order differential equation. Yeah. Okay, so I will maybe just add here that this is, this color is U or VL. I'm so sorry for always confusing V and U. And the light green is the current as a function of time, which is of course the same current here and there. And the dark green curve, just to complete this, is the voltage across this charging resistor. Okay, so yeah, what should we do next? Maybe form some differential equation and try to solve it. And we can think about other ways how to deal with this task. Okay, so we have 4 equations with 4 unknowns. We need to form one equation with 1 unknown. So I would suggest to, maybe do I have a light color here? So we could take this and insert it here, and take this and insert it there, and then we just have the same 2 currents. So we will get some first order ordinary differential equation, which says, okay, the source voltage, the constant source voltage, is the current, and I will maybe just write I of t, yeah, which makes it simpler. So the current multiplied with the resistance plus L times the time derivative of this current. So now we have one equation with 1 unknown, the unknown current. And it's a linear differential equation because we just have the function and the derivative of the function. We don't have a square or square root or what else. It's a first order differential equation because we just have the function and the first derivative. And it's, mathematicians would say it's an inhomogeneous differential equation because we have something on the here left side, or usually it would be on the right side. And if the right side would be 0, then it would be called a homogeneous differential equation. This is inhomogeneous. This makes it a bit difficult, more difficult to calculate a solution, but not dramatically, let's say. Okay, yeah, so now how do we calculate a solution of such a differential equation?
Initial conditions.
We need to have initial conditions later on. Yeah, and the initial condition is that the current at the time 0, yeah, so this is our IC initial condition, that the current at the time 0 is 0. This is what we said here. Current starts at 0. Say again?
Because the source of energy storage
Because, I mean, this is more here kind of a definition, because we said that maybe at the beginning the switch was open and then at the time 0 we flipped the switch over to the left, and if the switch was open before, of course, then there cannot have been a current before. Okay, so later on we will remember we need to have this initial condition. Okay, back to the question, how do we solve this?
You replace I by exponential.
Yeah, we look at so at first what we do is, at first we will homogenize this equation, and we will say, okay, we take the homogeneous equation and say, okay, our current multiplied with the resistance plus the time derivative of the current, it's maybe like write it like this. Yeah, so this is the time derivative. They should be 0. Why it's okay to have to let's say to delete the source? It's some kind of drastic change to our equation, but why it's still meaningful?
at time 0 the
No, it has nothing to do with the time 0. It's
Homogeneous?
yeah, because we would so calculating a solution to this is like the eigensolution, the own solution of the circuit. It's like, what would the circuit do without any source? And it's a bit like if we later on might want to think about second order differential equations. Yeah, where we have two different energy storage elements, like an inductor and a capacitor. Then you could think, okay, then if we form such a differential equation, there would be that the function plus the first derivative plus the second derivative should also be equal. So what would then be a solution for the second order differential equation? For which functions the function and the second derivative are equal?
sinusoidal.
Yeah, also for the exponential function, but also for sine and cosine. And that's why you get oscillations. For a second order differential equation, you get a resonant circuit. In electrical engineering, you get oscillations. And I don't have something really nicely here to demonstrate this, but I don't know if how good is this string here that is holding my T. So if you let's see how solid it is. Yeah, so now I have a mass and I can move it, and so it can also have two different forms of energy, namely height energy, let's say, and kinetic energy. And so while it's oscillating, it's always moving the potential energy against kinetic energy and vice versa. It's not a pretty good swing, but you can imagine how it swings. Yeah? And so I can also move it very quickly. So this is the source, I'm the source, I can move it very quickly, and I can move it very, very slowly. Yeah, but I can also try to make this as fixed as possible and let's say push it once, and then this is how it will move without the source. This is like the eigensolution. Yeah? This is the solution of the homogeneous differential equation. And this is kind of what we do now with our circuit. We calculate what does the circuit do without the source.
Calculating natural frequency.
Say again?
We're calculating natural frequency.
We are calculating natural frequencies, but in our case we don't have any oscillation so far, yeah, because we just get this exponential growth and decay. And now there was a pretty good solution. or suggestion, let's use an exponential function, because if we look at this, now what this equation tells us, what we also just discussed, is that the function multiplied with some factor plus the time derivative of the function multiplied with some factor, that together they always need to be 0. So the function itself and the first time derivative of the function must somehow be equal, otherwise they cannot always be 0 for all instants of time. So we can guess a solution, and the solution that we guess is some exponential function. And so if mathematicians guess a solution, they say we do an approach. And this is the mathematical term for guessing a solution. And we take an approach with some exponential function. So we say I of t is an exponential function that depends on time, right? Okay, looking not too bad, but still looking not too good. Why can this not be a solution to our equation?
Minus and the coefficient.
Yeah, there must be something here, and at the end we will find out that this also needs to be negative.
Should R be there?
Yeah, so we need to add something to this solution, and one there's an idea.
The coefficients of...
Yeah, we need to have some. So we need to add something at first. I mean, we are so mathematicians would say, okay, this is somehow looking nicely. Why not? Yeah. Maybe okay. Mathematicians would find other reasons why we need to add something. But as an engineer, as half a physician, no, physicist, right? Or what is physicist? I'm not a doctor. As a physicist, I would say, but just half a physicist. I would say we want to calculate a current, and the current at the end should have the unit of a current, should have the unit ampere. If we look at this, the time has the unit second, but we can only calculate e to the power of a number. We cannot calculate e to the power of a unit. So we need to have something here that, let's say, that we call lambda, so that the unit of lambda is 1/2, so that the unit of lambda and the unit of the time will cancel each other, will be unitless, will be just a number. So e to a number is a number. Still, we want to have a current. So?
R over C. R over L.
Yeah, we need to have something that will give us the unit of a current. And so we need to have two numbers, not two numbers, two quantities that we call lambda and k. And the unit of this k at the end should be 1 ampere. And then it makes sense. Looking at the units, right? This is unitless, e to something unitless is unitless, and then multiplied with something in ampere gives something in ampere. Okay. So this is one rationale why we need to have k and lambda there, or two other quantities. And the other reason, or another reason why we need to have these two quantities there, is that we somehow need to make this solution fit to our equation. Yeah, we need to we have the solution, and we need to zoom or let's say stretch and squeeze the solution in this dimension, and we need to stretch and squeeze the solution into this dimension. And what does the k do? Stretches and squeezes, but in which direction? If you make k larger, what will happen to the function? It will do vertical scaling. And what does the lambda do? It will do horizontal scaling. Yeah, and this is the reason why we also need to have the two quantities there to make our solution at the end fit to our problem, to our circuit, and so on. Okay, so this is our approach. Now we can also calculate, of course, the time derivative of this approach and say, okay, the time derivative of this exponential function is, once again, the exponential function. And k is a constant factor, so the factor rule tells us we just need to copy the constant factor. And then what happens as well? Is this the full time derivative? No? What is missing? Yeah, it's a nested function, so we still need to multiply with the time derivative of this inner function, and this is lambda. And yeah, this also then makes sense from the units, yeah, because the time derivative, like if we look at this here, it should have the unit ampere per second, and so this has the unit ampere, and this gives 1/2. So this totally makes sense. And now I don't have much space here because there's my camera window, so I need to go over there. What we do now is we take this and insert it here, and we take this and insert it over there. And then we get from our first order homogeneous differential equation, we get that k times e2 lambda t multiplied with r plus k times e2 lambda t multiplied with lambda multiplied with L equals 0. And this is the so-called characteristic equation. And from this equation, we can calculate lambda. Because in this equation, we can say we can divide by k. We could not divide by k if k could be 0, but k shouldn't be 0. If k is 0, then the time function is 0 and the time derivative is 0. Okay, this would be a solution to this equation if everything is 0, but it would be a trivial solution. It would not be a meaningful solution. And so k should not be 0. That's why we can divide by k. And we can also divide by the exponential function because the exponential function also does not get 0 as well. So we get that r plus lambda L equals 0. And so from this we can calculate lambda and say lambda is minus r divided by L. Right? And so here we get the minus that you would like to have or someone would like to have at the beginning. And we also get something with r and L. And we can check now if we calculate the unit of this lambda. What is the unit of the resistance? Ohm. Ohm. And ohm can be also written as volt divided by ampere. And what is the unit of the inductance? It's Henry, and Henry can be written as Siemens per second. Yeah, but the other way around. A second divided by Siemens, I would say. But Henry is volt second divided by ampere. Yeah, and so now, and this is like second divided by Siemens. But the amperes will cancel each other, the volts will cancel each other, and we get 1/2. And this is also what we said here at the beginning, that the lambda should have the unit 1/2. And there is a question.
I'm sorry, it's a trivial question. But,
there are no trivial questions.
Were the e functions removed because we're dealing with time equals 0?
No, the e functions are removed because the exponential function can never be 0. So we can divide by the exponential function. Yeah, and on the other side, here we would have something like divide by k divided by e2 lambda t, which is can hardly be seen, but yeah, and so 0 divided by something that is not 0 and divided by something that is not 0 is 0. And so that's why we are then really just left with r plus lambda L equals 0. And we get lambda. So from our approach, we already got lambda. Yeah, we have already calculated the lambda. And this is minus r divided by L. And there's another question.
We got rid of E at first because t is equal to 0.
No.
Okay.
We just divide by this function for any instant of time, and for any instant of time e2 lambda t is never 0.
Okay.
And so we divide by this, and then as said, so on the other side of the equation it's still always 0. And that's why we get rid of the exponential function. And because we don't have this here has nothing to do yet with our initial condition. Okay, so we have calculated lambda already. So we are still missing k, and we are still missing somehow that we have just had a look at the homogeneous differential equation and not on the full differential equation. So this is only part of the solution, let's say. This is just the solution of the homogeneous differential equation. Okay, so now we need to have k, and we need to have a solution of this inhomogeneous differential equation. And looking at the inhomogeneous differential equation, the easiest solution for this is to say what will happen. Yeah, so I think this is called the particular solution. And it's not the voltage that we want to calculate, it's the current. So the particular solution of the current is, let's say, the current if the time gets very large. And this works in this case. This is not, let's say, something that generally works, but for all the engineering problems that I know and that we deal with in these types of lectures, it works pretty well. So we let the time go to infinity. We wait, let's say, until the charging and discharging, and so it's done. So if the time goes to infinity, and then we can look at what we discussed before, then the current will not change anymore. And if the current will not change anymore, what happens to this time derivative? It will be 0. So everything that we are left with is voltage times resistance, current times resistance is voltage. So we can say that the current in this case will be the source voltage divided by the resistance. Looking at this equation. So now we can write down a total full solution. And the total solution will be I of t is our homogeneous part of the solution plus this particular solution, and this will be k times e2 lambda t, and we know the lambda already, and then plus source voltage divided by resistance. This will be the full solution, and now the only part that is missing is the k. So where do we get the k from?
We set I to 0.
Yeah, this is what we get from the initial condition. And so if we now insert our initial condition here and say k times e2 lambda multiplied with 0, right? If the time is 0, then plus v source divided by the resistance. And this at the end should be 0 because this is our initial condition that it should be 0. So e2 0 is 1. So k should be the same as this, but just with a minus. Yeah, so we get at the end that this is minus Vs, and here we have plus Vs divided by R, so we get V source divided by the resistance multiplied with 1 with this term, and then minus the exponential function 1 minus e2 lambda t, and instead of lambda I will now write R divided by L multiplied with t. And so this will be the full solution of our differential equation in this case, yeah? Along this way. And this is like, it's a little bit like a recipe. You need to know about the recipe. You still need to know how to apply it, but at the end you also need to memorize this recipe if you want to do such solutions. Okay, more questions so far. So then, of course, now what we can do is we can, I mean, we could quickly check that the k, yeah, so from this equation here, we said, okay, k is minus Vs divided by R. So if we take a look at the unit of this k, we get volt for the voltage and ohm for the resistance, and ohm is volt divided by ampere, so volts will cancel each other and we get ampere, what we said here, which also nicely makes sense. Yeah, and so now this is the time curve. Maybe what we can do now is we can plot it. So I will take Octave and make my mouse went to sleep, make the Octave window a bit smaller, and try to move it in a way that I get here the values at first. And okay, we did not really set meaningful values, but we can just copy them from the task and say, okay, our source voltage is 500 volt, which is maybe quite a lot, but we will use it anyhow. Yeah, and the charging resistor is 0.8 mega ohm. Maybe we should use different values. We will leave it as it is. And the inductor, so here it's 10 microfarad. I would just use 10 microhenry. But I think, no, this at the end will not be meaningful. So let's use different values, because I think then we don't get anything really meaningful out of this task. So I will use blue once again and say, let's use a much smaller voltage here. Let's use something like 12 volt, maybe like a car battery, classical car battery. Let's use a kind of small charging resistor. So maybe just 0.8 ohm, no mega ohm. And then let's say that the inductor L is, yeah, maybe 10 millihenry, which might be meaningful. And there's another question.
You just had to do with the algebra.
With what?
With the algebra.
Okay, with the calculation, okay. So, forget about what I've just typed here. We will use other values. We will use 12 volt, like a car battery, charging resistor, pretty small, 0.8 ohm. Maybe just like the inner resistance of the car battery plus some cables. And the inductor, if I move this further to this side, 10 millihenry, which is, yeah, not too large, not too small, like a usual inductor, I would say, where you have some windings around some iron core. Okay, so now we could calculate our lambda here, and lambda is minus R divided by L. Oops. And then we get minus 81 over second. What is usually the more interesting quantity is to use the so-called time constant that I will call tau. And so the small Greek lowercase letter tau. And tau is minus 1 over lambda, and in our case it's L divided by R. And so if I say here, okay, tau is minus 1 over lambda, I get something, or if I say tau is L divided by R, then I also get the very same quantity. And this is 12.5 milliseconds. So now we get something that really has the unit of time, which is usually more meaningful than this lambda, let's say. Yeah? So something should happen in 12.5 milliseconds. Okay, so then we can try to plot this time function here that we have at the bottom for our current. And for this, of course, I need to have a time range. And my time range should be linearly spaced. So I will use a lin space vector starting at 0. And then what would be a meaningful end time so that I get a similar plot as the one that we see here at the top?
4 tau.
4 tau, 5 tau, 10 tau, something like this. So I will use 10 times, or maybe 5. 5 times tau. And I will use, I don't know, 101 values. Or maybe 501, something like this. So this should give nice time steps. Yeah, and the semicolon omits the output because otherwise I would now see a 500 values here in my command line. And yeah, so then we can say that the current as a function of time is V source divided by our charging resistor. So here maybe I need to add the RC. Oops. Okay, something strange happens. Divided by RC multiplied with 1 minus the exponential function of minus lambda times t. No, not minus. The minus is already included in the lambda. Lambda multiplied by t, and then parentheses closing for the exponent, parentheses closing for the function itself. And omitting this output, and then you can see that I also get 501 values. I inserted 501 values for the time. I get back 501 values for the current. And now I could plot this and say plot t and I of t. And then it takes some time, and then we get our time function for the current, which looks pretty similar to what we have just drawn by hand before. Okay, if we know, so what could we do next?
Track 3 tau.
Yeah, we could, so tau would be somewhere here. 2 tau would be somewhere there at 25 milliseconds. Here would be somewhere 3 tau, 4 tau, 5 tau. This is because this is 5 tau what we calculate. I mean, what we could do is we could calculate this voltage here, because now if we go back to this equation, now we have the current. If we calculate the time derivative of the current, we should get this voltage. I maybe have some space here to add this voltage. So it should be L times the time derivative of this function. So if we calculate the time derivative of this function, it's this constant factor at first. So V source divided by RC. Yeah, and then we have a sum. And the rule for sums tells us every part of the sum we can calculate the derivative individually. So the first part of the sum is constant, and the time derivative or derivative of this is 0. And here once again we have
minus R over L.
Yeah, we have some exponential function. So we get a minus, then we have E2 minus R divided by L times T. And then we also have,
minus R over L.
yeah, minus R, we have this inner derivative. So the minus and minus will cancel each other and we'll have a plus at the end, and then we have R divided by L. So this L here and this L there will also cancel each other. And this is the same RC, so this RC and this RC will also cancel each other. And we will just get the voltage. So we get that the voltage is source voltage multiplied with E2 minus R divided by L times T. And so now we can plot this also, add this to our octave window here and say VL of T is source voltage multiplied with the exponential function, and it's once again lambda multiplied with T. Yeah? And then I can have a second plot, maybe figure 2, and in the second figure plot this voltage across the inductor as the function of time, and look back in my second figure, and then this looks like this, and this also looks like the red curve here on the other side. Okay, so now we have the second voltage. How do I get the voltage across the resistor? Pretty easily, formula is already there. Now I just need to take the current, multiply the current with the resistor, then let's say this resistance here will cancel. So I could say that the voltage across the resistor as a function of time is Vs multiplied with 1 minus the exponential function of lambda multiplied with T. I need to move this a bit to the other side so it's not hidden behind my camera window, and do this. Yeah, or I could also, I mean, we can plot it, hold on. Let's make sure that this window is the active window, hold on, and then also plot as a function of time the voltage across this resistor. And we get the two curves there. And now it's a bit confusing because what is blue here is red on the other side and what is green here is red on the other side. But yeah, it's understandable, right? You get the idea. And so if I take a look at the first 10 values, so you see there the first 10 values. Maybe we can make this a bit smaller here, this side. And so if I would have calculated this voltage just by the resistance, the charging resistance times the current, and once again output the first 10 values, then you see I get exactly the same values and the same quantities. So of course this way of calculation would also work, yeah, because this is exactly the equation that we have written here at the bottom. Okay, so yeah?
How did we just differentiate I of t to get v?
Yeah, sure. We just did this. You mean numerically? That's a good question. So there is a command that does numerical differentiation. Yeah, so it's if we insert x as a vector, then it's the vector of the first differences of this. So we could say, okay, our voltage across the inductor as a function of time that we get by this diff, by this numerical differentiation, is we have the diff of the current. Yeah, and we still need to multiply with the inductance. And this diff is just the the diff of the current. Yeah, so it's like a delta I, but we also need to divide by delta t. So I think what might happen, let's see if it works, is if we say divide by diff t and omit the output. Okay, and this worked. Yeah, and so if we check here on this side, then here's the result. But now this only has the dimension going to 500, because if you have, let's say, 10 values, you can only calculate 9 differences. So you always lose 1 at the end. So if we would plot this into the same, yeah, so if I add up a third figure, figure 3, and now if in this third figure, maybe I can move windows side by side. So if in the third figure we try to plot our original time and the voltage across the inductor that we calculated before, which was the perfect solution, then this is what we had before. Right? This was including the exponential function. And now I once again say hold on and go to plot and now say I just want to have the first 500 points of the time, because this here that we get by, well, how did I call this? VLT diff. It's really not working. Okay, parse error. T1 to 500 and then VLT diff. Yeah. And then you can see that now the blue curve and the red curve are almost perfectly on top of each other, because this also works. And we can also, by this way, here calculate this derivative numerically. Okay.
So why did it work physically though?
Why did it work physically? Because this is the law of induction. We've just checked that the law of induction works. Okay. Anyone an idea for a last check that we could do? If I go back to my plot window 2 here, which was this one. So here we had the voltage across the resistor and the voltage across the inductor. If I calculate the sum of the two, what should happen? Yeah, we should get the source voltage. We should get something constant, and that is 12 volts. Yeah? So we can try this out and say our source voltage as a function of time, yeah, is the sum of the voltage across the resistor plus the voltage across the inductor. And we get 500 values. And if I'm into figure 2 and once again say plot Vs as a function of t, Oh, now it plotted into figure 3. But okay, it's a constant. It's working. Yeah. So we get a constant voltage and we get the 12 volt that we put into into this circuit. Okay, so we have calculated the time course of the current and voltage during charging. We can say check. What is the maximum charging current? Here it's more like what is the maximum voltage that we get, the maximum charging voltage we have also calculated is this K here. This is the voltage that we get at the end. If we wait long enough, this will be the maximum charging current, and charging voltage, okay, is the source voltage. The maximum voltage that we get across the inductor is at the beginning, and it's the source voltage. So, okay, maximum current is the current at the end, maximum voltage is the voltage at the beginning. Check. After what time it's practically finished? 3 tau, 3 times this time constant, I don't know, maybe 4 times, maybe 5 times, maybe 10 times. I would say, I mean, what we have plotted here is 5 times. You can see that it still increases a bit, but it would be very difficult to measure already, right? If you have 12 volts and if you want to measure the difference here of, I don't know, 10 millivolts or so. So some multiples of this tau, depending on how exactly you want to have it. Okay. Check. So now we flip the switch over. And if we flip the switch over, then we just have this mesh. And so maybe to make it not super confusing, I will invest another slide here and maybe copy at least the schematic once again and maybe the last tasks here. And insert this, and then we can think about a little bit what happens now. So remember, this is still our inductor. So instead of C, we have L, and now we flip the switch to this side. Yeah, so we have a discharging current, and I would rather try, because we had the current before in this direction, and remember that the voltage across the inductor as a function of time is L multiplied with the time derivative of this current. So because of this equation, this current cannot jump. It can only smoothly change. So if we flip the switch over, which really needs to happen instantly, and because if the switch is stuck in the middle, there can be no current. Yeah, but we would need to flip the switch instantly. We can remember me that we discussed what will happen if we don't flip the switch instantly. But in theory, we flip the switch instantly, and the current will just continue. And so the current, because now it cannot go to this side anymore, the current cannot close this loop, the current needs to close this loop. So the current will go this way, will go this way, and will go this way here, will go the other way around. And so therefore we will also get, yeah, a voltage across this resistor that is pointing upwards, let's say. So we have this voltage current relationship here. We have the same voltage current relationship at the resistor as before, multiplied with the current. And then, okay, the Kirchhoff's current law would be just that the currents are equal. We don't write this down explicitly. And then we have, yeah, or I could say Kirchhoff's current law is saying, okay, the current at the one side of the equation is the same as the current on the other side of the equation. And Kirchhoff's voltage law would tell us in this mesh,
voltage in R plus voltage in L.
Yeah, that the sum of the voltages should be 0. Yeah, and now we could, like before, say we will take this equation inserted here, take this equation inserted there, and then we have once again our first order. I will write the time derivative like this: first order differential equation. And this is now directly homogeneous. And we can do the same solution that we did before. Yeah, and now we know already, okay, the solution of the homogeneous equation will be k times e to lambda t, and lambda once again will be minus r divided by L, like before. Like if I would go one, it's not working, so I will better not. Yeah, you know what I mean. Now it's once again broken already. Okay. So this is our lambda. We need to have k, and we need to have this solution of this, or the particular solution, which remember was we wait for a very long time. So if we here wait for a very long time, what will happen to the current? The current will be 0. Okay, so now our full solution is the sum of this and this. We can omit the 0. Still, we need to have the k. And where did we get the k from? From the initial condition. So now the initial condition in this case, so if we once again say we flip the switch over at the time 0, but before the switch was long closed on this side, now the current through the inductor at the time 0, at the time where we flip the switch, would be?
Charging current.
Say again?
The maximum current.
The current that we had before. The maximum current, and this was source voltage divided by the charging resistance. Okay, yeah, so, and then this will be the k here. Because yeah, this is then if we insert so if we once again say, okay, this is now k times e to lambda multiplied with 0, and e to 0 is once again 1, so directly it stands there that k must be this. Okay, so now we have also written down the full solution, and I will maybe write it down here. So the current is V source divided by RC, source voltage divided by charging resistor, and then multiplied with the exponential function. Yeah, but here we need to be careful. This is a different lambda because this is a discharging resistor, right? So it's E2 minus R discharging divided by L multiplied with T, or discharging lambda. Okay, so now what we can do is we can go back to Octave, and we need to set some discharging resistor. And I will select for the discharging resistor. So remember, our charging resistor RC was something quite small, 0.5 ohm. Now for the discharging resistor, I will use something much larger. I will use, let's say, 1 kilo ohm, 1 E3, 1000 ohm. So now we can calculate, of course, our new lambda, the lambda for the discharging. As it's written here, it's minus discharging resistor divided by L. And now we have a much larger resistor than before. Does this make sense? Yeah. So we get a much larger lambda. And we can also calculate the tau, the time constant for the discharging, which was 1 divided by, or minus 1 divided by lambda. So if the lambda got larger, what should happen to the tau? Should get smaller. So now we have something that is just 10 microseconds. So we are charging in some milliseconds. We are discharging in some microseconds. Okay, and so I think we have everything here that we need. So now I can say L for discharging as a function of time is source voltage divided by RC Yeah, or maybe we can calculate this before. So the maximum current is source voltage divided by charging resistor. 12 volt divided by 0.8 ohm should be, I don't know, 15 ampere or something like this. Yeah, so we get 15 ampere. Okay. So now we can say, okay, the current, the discharging current as a function of time is this maximum current multiplied with the exponential function and then lambda for discharging multiplied with time. And so now I also probably need another time frame for discharging, because this discharging happens a bit faster. So I will enter, there will be some error message, we will define this time and say, okay, this will be a linearly spaced vector between 0 and 5 times tau for the discharging, and once again 501 values, and then I can copy the line from before, and I will close all my plots because now we have enough plots open, and just again plot the discharging time and then the current during discharge. And what would you expect? Yeah, like exponential decay. Yeah, so we are starting with the 50 ampere, and then it's exponentially going down, and now everything is happening much faster. Okay. No surprise yet, I would say. So now let's calculate this voltage here. And maybe let's calculate this voltage here. So what we can do is we can say, okay, the voltage across the inductor here is L times the time derivative of the current. This is a constant factor that we can copy. And then we have the exponential function. The time derivative of the exponential function is once again some exponential function and multiplied by minus RD divided by L. So the L will cancel each other and we get this function. And we can also calculate the voltage, here the voltage across the discharging resistor. And then we get RD multiplied with the with this function, and we can see, okay, this is RD divided by L multiplied with T. Yeah, so it's the same. It's the same term, but this is negative, this is positive. Yeah, here's the RD, here's this is the maximum current, let's say. We have the same exponential function. So here we have a minus, here we have a plus. So the sum of the two should really be 0. Okay, so we can check this out, go back to Octave and say, okay, VL for the discharging as a function of time should be the maximum current multiplied, or minus the maximum current multiplied with this exponential function, lambda d multiplied with discharging time and multiplied with the discharging resistor, yeah, and plot it. And I can do the same for the voltage drop across this discharging resistor. It's the same formula but with a plus there. And then, I mean, we can imagine that the sum of the two is 0. So now let's once again have a second figure, and let's plot these two voltages into the second figure. So plot the discharging time on the x-axis and then the voltage drop across the inductor, and once again the time and then the voltage drop across this discharging resistor. And what would you expect if I press enter on my keyboard? How should it look like? So remember,
As Vn starts from 0.
this is how the current looked like, and the voltage across the resistor should be just proportional to the voltage, and the voltage across the inductor should be the inverse of this. So if I press enter and plot it into this figure, and we see this is the voltage drop across the resistor, which is the second quantity plotted in red. This is the voltage drop across the inductor, which is the negative function plotted in blue, the first function. Okay, and the sum of the two, as you can see, as you can imagine, is 0. How it should be in this one mesh that we have here. Okay, so do you see something else that is maybe quite interesting?
Voltage drop is kind of like current drop.
Of course, the voltage, the time function looks similar because this is what our what is written here, Ohm's law. We see Ohm's law, but what else do we see? Of course, we should say again.
The reverse of that.
Yeah, we should maybe label our axis, right? If we are good engineers and good physicists, we should label our axis. This is the time in seconds. This is the current in ampere. This is the time in seconds. This is the voltage in volt. So, we get 15 kilovolt. Well, how do we get 15 kilovolt?
Oh yeah, the current discharge in the
conductor. We have taken a pretty small source, like a car battery, and we were charging some inductor in some milliseconds over some quite small resistance, because this would just be the inner resistance of the source, the inner resistance or the resistance of some cables, and the ohmic resistance of the inductor of the coil. And then we reach, because we have a not so strong source, but also not a so large resistor, we reach a reasonable amount of current, which is 15 ampere. We reach the 15 ampere that we see here. And now we flip the switch over, and now the inductor wants to push this 15 ampere of current. It needs to push it, because this is what the equation here says. The current cannot instantly drop. The current needs to continue, but now the current needs to go via a 1 kilo ohm resistor. So from the 15 ampere in the 1 kilo ohm resistor, we get 15 kilovolts. Just for a very small amount of time. It's just, what is happening here, it's just microseconds, just 10 microseconds, but we get, for a very short amount of time, we get a very high voltage. So what have we built now?
Transformer?
Nah, not really, because a transformer usually would work with sinusoidal currents and voltages. It's a bit like this electric, for example, ignition for cars, something like this. But there you would, but not the starter, because the starter is an engine, but the spark to generate something for sparks, or to have something if you have cattle on a meadow, and if you have this electric fence around them, then there would be also some relay that flips a switch like this, charging and discharging, charging and discharging some inductor, and discharging it over the electric fence. And then the kettle touching the fence would be the resistance, then getting some electrical shock and staying away from this electric fence, more or less. So this could be some application from our circuit that we just discussed, that we can make a small voltage via a current into a large voltage. But of course, we cannot, we have still the law of conservation of energy. So yeah, we need to charge longer, and then we just discharge very quickly with the higher voltage and the same current and so on. Yeah, so if you would calculate power and so on and energy, of course, the energy here that you store will be the same energy that is dissipated there. And so if you get higher voltage, still the same current, you need to have less time. And if we would look back on to the original circuit with the capacitor, yeah, here it's, as I said, it's everything is similar but opposite or totally different. Here we would have a rather large charging capacitor. We would or charging a rather large charging resistor. It would also take longer time to charge the capacitor, but then we could discharge the capacitor that stores the voltage. So here we charge it up to 500 volts, but from a weak source that has a very, very high inner resistance. We charge this up to 500 volts, but then we discharge over a quite small discharging capacitor. So here we would get not a high voltage, but a high current. Yeah, and this is from an electrical point of view, go away. This is from an electrical point of view, it's a bit like, let's say, flushing a toilet. Yeah? You have something in the toilet, but you have just a very weak supply of water. And with the weak supply of water, you cannot flush something away that is there in the toilet. So you're having like a storage for charge, like a storage, a reservoir for water. You charge it up, and it can take a minute or two or whatever, and then you push the button and you flush, and you flush it with much higher current flow in a shorter amount of time, and then you can flush something away. Yeah, and this would be a mechanical analogon of this circuit. But what you could use this circuit for is, for example, a flashlight. You have a weak battery, and from the weak battery you cannot get a bright light. But from the weak battery you can charge a capacitor over some seconds, and then you can discharge it in milliseconds, and then for some milliseconds you get a high current and you get a high flash or a bright flash. Yeah, and so this would be some application of this circuit and some other application of the circuit that we just discussed. And I mean, what you could also do is, if you have LT-Spice, you could also simulate this in LT-Spice. It would not be too complicated to do so. And another way to do this or to solve this task is a little bit what we have done at the very beginning. If I go back to my first slide here, so you could just take these four equations, and from this equation with the real time derivative, turn this di by dt into a delta I by delta t, and then just take small time steps. And for each small time step, just apply these four equations inside a loop, and then you will also get the same curves or similar curves for current and voltage. And this would be also a numerical solution of this ordinary differential equation. What we have done is an analytical solution of this differential equation. And the analytical solution, to be honest, is only possible in these very simple cases. Maybe for a first order, maybe for a second order differential equation, and for not too complicated circuits. And these numerical solutions, also what LT-Spice does, they are possible, of course, also for more complicated solutions, but you never know. Are you doing it right? Are you doing it wrong? Garbage in, garbage out. So it's always nice to have such an example like this, where you can do an analytical solution that you have something to validate with your numerical solution. And then once you did this validation, and if you're pretty sure that your numerical solution works, then you can also apply the numerical solution to more complicated problems and to more complicated circuits than the ones that we have dealt with in this exercise. But this is nothing that we will do today anymore.